All right, let's finish up chapter 19. We're talking about inflections and shape, concavity. Let's go. If we have a curve, it's got anything looking like this, where it's kind of bending downwards as we move from left to right. We're going to say that shape is concave downwards. I just say concave down. This guy right here, we're going to say that that's concave up. Now it doesn't need to be like a parabola. I mean, if we just have the like an exponential growth graph, that's concave up because you can see that it has kind of the shape of like this part here. Likewise, an exponential decay graph, also concave up because it's kind of just got that basic shape to it. Doesn't have to have both an increasing and decreasing part. I taught a student once who insisted on saying, instead of concave up, he would say convex down. Okay, if you want to be like that, I guess it's correct. Those are both antonyms. I don't know. Don't be like that. I realize by saying that now, one of you idiots is going to insist on doing that in all my classes, but so be it. Okay, so we want to try to figure out what the shape is. Well, let's just think for a second before we see what the rule is. If we have a concave down curve, let's look at those slopes of the tangent lines. They start off over here really positive and quite steep, and actually as we move farther to the left, they'd even be getting steeper. As we move to the right, they're still positive, but they're less steep. Eventually they become 0, then they became negative, and then they're becoming more negative and even more negative. What that means is that our derivative is decreasing. Now, when our function is decreasing, our derivative is negative. So if our derivative is decreasing, that means that our second derivative is negative. And likewise, down below, if it's concave up, then our derivative is increasing, which means that our second derivative is positive. So that's what concavity is all about. Our graph is concave down if the second derivative is negative, and it's concave up when the second derivative is positive. Where that concavity changes is called a point of inflection. So we've got two pictures here. This one on the right, this one's actually a stationary point of inflection. We talked about that in the last video. That's a point of inflection where the tangent line is horizontal. Not every stationary point is a point of inflection, and not every point of inflection is a stationary point. So finding points of inflection means we're going to be taking derivatives, and then we're going to be taking the derivatives of those. So we're taking second derivatives and finding out when they are equal to 0, and we have a sign change. Our sign of the second derivative needs to change either from positive to negative or from negative to positive. That will indicate a change in concavity or change in how the graph is curved, which means that we have a point of inflection. So that's our plan. But of course, there are some, some weird situations. Let me just get the wacky ones out of the way first. What would happen if we had a second derivative equal to 0, but there's no change in sign? So let me just give you an example of that right now. Let's look at x to the 4th. So we calculated second derivative, that's 12x squared. Clearly, that's only equal to 0 when x is equal to 0. But if I choose any value to the left of 0 or to the right of 0, I'm clearly getting a second derivative which is positive, and that matches up with the picture that we see at right. So x equals 0 is not going to give us a point of inflection. What's happening graphically here? I don't know. It's like extra flat. I don't have a good answer for you. Perhaps you can investigate. And here's an example where in the last video we talked about checking first derivatives for maxima and minima, but I said, hey, the first derivative doesn't need to be 0 at those points. It could also not exist. So here's one where the second derivative does not exist, but we still have a point of inflection. So x to the 5/3, we calculate its second derivative, and we've got 10/9 x to the negative 1/3. Again, clearly, second derivative could only be equal to 0 when x is equal to 0. But now if we choose any value to the left of 0, then we've got a negative value. We're taking the cubed root of a negative, which is fine. We can do that, but we're going to get a negative to the left, and we're going to get a positive to the right. So we do have a change in concavity here, even though the second derivative itself does not exist, which is kind of weird. Again, the IB is not going to focus really very much on weird stuff like this, but it's something to keep an eye out for. All right, so let's do one. Now, in practice, again, with like AP or even, I think, IB questions, you're not really going to be prompted to like go through all these steps to get there. The question is more likely to just say, hey, here's a function, sketch the thing. But this is the process we need to go through. We're going to need to find any maxima or minima. So that's finding our stationary points where the first derivative is equal to 0. We're going to have to find any points of inflection. And then we're going to have to, try to draw the thing as best as we can. So let's go through this example together just to see what that process might look like. This is a quartic function. Quartics can look weird, and okay, up to this point, there's no way that you would really be able to graph this thing without the use of a calculator. I don't know, you could like put in some random points for x just to see what happens. I know the y-intercept is -9, cool, but the rest of it is not. I know the y-intercept's -9, I know it has that basic shape, but other than that, yeah, we wouldn't know what to do. But now we do, so let's do it. So for starters, where is the derivative equal to 0? Okay, so we've got our function. We're going to find its derivative. We're going to set it equal to 0. We're going to factor. We're going to get a sign diagram. This is great. This tells me that when x is equal to 0, we've got a minimum. And when x is equal to 2, we have nothing special. We have a stationary point of inflection. So already I know I'm improving my picture. It's not going to look like that. It's going to look kind of like that. Of course, we should find the associated y values with those two x values. So we just put 0 and 2 back into the original function to get the y coordinates. Okay, next we're on to part B. We just found one point of inflection, but there might be more. And yeah, if we look at this picture here, it certainly seems like we're going to have another point of inflection. Let's see, we're concave up, we're concave up, we're concave. Oh, right around here, we're switching to concave down. Then we have our other point of inflection, go back to concave up. So it looks like there's going to be a second point of inflection, which will be non-stationary to go along with 2, 7, which is our stationary one. So we take our first derivative, and we're going to find the second derivative from there. You could use this part, this form of it, if you want to use the product rule, but I think it's probably easiest just to use the original first derivative we found, since that's still polynomial. Calculate the second derivative, set that equal to 0, work out what the zeros are, make a sign diagram. Great, we get 2/3 and 2. Choose values around there. 2 we already knew about, and that's changing from, the second derivative is changing from negative to positive, and that matches the sketch that I put together earlier. And at 2/3, we're changing from positive to negative. Wonderful. We should figure out the y coordinate for that 2/3 point. It's roughly -2.48. That's the best we're going to get. So we've got one stationary point of inflection and one non-stationary. I should have said earlier, I'm sorry, I mean, I remember the general shape of the graph should be like this from studying in chapter 6 with polynomial stuff. But even if you've forgotten all that, we're going to get this picture in just a minute from doing all this calculus work. So if you don't remember that, that's okay. You don't need to. All right, so now letter C, what did it even say? Find where it's increasing and decreasing. Well, we've already kind of worked that out from the sign diagram of the first derivative, right? It's this function is clearly decreasing for x less than or equal to 0, and it is increasing for x greater than or equal to 0. And there's not really much else to say about that. For part D, that was asking for the concavity. Again, we have that information from the sign diagram for the second derivative. It's concave down, just in between 2/3 and 2, and it's concave up otherwise. And then from all of that, we could easily sketch the graph. I say easily. Let's actually look at what that might be in practice. So here I've just collected all the... Damn. So here I've just collected all the information from the other screen that I'm going to use to sketch the graph. I just need to know 3 points, because those are the only points that I can work out, and the sign diagrams for the first and second derivative. Now, we got the y-intercept here because the x equals 0 was one of the values for 0 for the first derivative. Had that not been there, of course, I would have identified from the function itself what its y-intercept is just by putting in x equals 0 into the function. That's a really helpful point to have. So if I wanted to sketch this thing, I don't know, let's just put some things down. This does not really need to be drawn to scale. We just want it to be kind of there. 2, 7 is good. Okay. And of course, if I had the some information about the x-intercepts, I'd want to include those too, but I certainly don't have that here. All right, so there's, I don't know, there's not like a right order to go about doing this. I'm going to start off by just drawing in that I do have a minimum when x is equal to 0. So I'm just going to jot that in there, and I know that I have a stationary point of inflection at x equals 2. So I'll just kind of make that a little flat there. The way the little smiley curve that I drew there makes sense because I know that at 0 my concavity is positive on both sides of it. Let's just fill in to the left of 0 now. This is a decreasing function to the left of 0, but it's always going to be concave up. So I just want to continue that basic shape. Now, in between 0 and 2/3, my function should be increasing, and it should still be concave up. So I want to continue that smiley face to that point. There, things are going to change. In between 2/3 and 2, it continues to increase, but we no longer have the smiley face. We now have a frowny face. It's concave down. So I change the way that my curve is bending, and then at 2, the concavity changes again. We continue to increase, but now we're going in that way. And that's the graph we'd get. Obviously, I'd label the points that I found, but that's it. That's it for curve sketching. Now, that's one example. We're going to work on a whole bunch of other ones in class together. But that's basically the process. You're going to find the first derivative, you're going to find the second derivative, and you're going to make sign diagrams, and you're going to use that to sketch. I like to stack my sign diagrams on top of each other like I did here. So I kind of had like my 2's were in line with each other. My 0 and my 2/3 were relatively in the right place. We don't need any sense of scale here, but I like seeing the numbers in the correct order. That helps me kind of just visually check as I'm sketching the function, is that matching the information in the sign diagrams above? And that's it. That's it for this entire chapter. It was all building towards being able to do this, which again, I don't know, this function was like not super tough. It was just a quartic, but like we can do really complicated graphs now. And I don't know, that is pretty neat. I think maybe you disagree. You're wrong.